Good morning. Can everyone hear me, right? I've had a small bit of change in my plan for teaching this. I was planning on giving you a very intensive lecture today, but I'm just doing tutorials tomorrow. But I've looked at some of the revisions last night, and I've decided to change that slightly. So I'm going to give you quite a short lecture first. Give you some time to do some tutorial questions, but I'm going to go over question 4, 5, and 6 because I found them a little bit complex. So there's quite a bit of maths behind them. You can do them graphically, which is a lot easier, I assume. How many people have tried 4, 5, and 6? 4? Can I get hands? 5 and 6? Okay. So I'll get there, but with question 4, you need to do a little bit of proof before you actually can calculate it. I thought it was, I just looked at it the engineering way and got to the answer, but you need to go through the proofs. With 5 and 6, you can do it mathematically, which is a lot more difficult, but it's more accurate. And I'll go through the mathematical method, and I'll give you a tip for how to do it graphically. And then I'll give you some time to do these tutorials, including all the way to question 8, if I remember correctly. And then we'll sort out the rest of the questions later. Tomorrow, I'll be doing I'll do a short lecture, finish this topic, and then let you drive all the equations. But it will be more of a workshop, so I'll put you in groups. I'm going to get you to drive the equations in groups, and I'm going to have another person with me at PhD. He's just finishing his PhD in thermodynamics in IP, so he's quite good. And basically go over with you guys how to get, how to drive all the equations. I'm not a big fan of driving equations. I wouldn't personally put it in exams, but this year I'm only setting 2 of the questions, probably. So it might be in your exam, so I want you guys to know it quite well. And I personally have never used them, and I have a PhD in thermodynamics, but you do use them in your exam, unfortunately. So I'm going to start with adiabatic processes. I'm going to ask some questions as well while we're going through it, not many hard questions. And then get you to do the tutorials. All okay? And everyone's happy with that plan? Yes? Okay. Just want to try group workshops, see if it works better for you guys for driving all those ridiculous equations. So, everyone, I assume, remembers the volume work equation by now, the integral of PEB. But what is an adiabatic process? In an adiabatic process, you have no heat exchange. So delta Q equals 0. So there's no heat going out, there's no heat coming in. But your T is not constant. Right? In a closed system, your T will change. Now, this change could be infinitesimal, or it could be quite large based on the amount of work done. Repeating this for some reason. So the first law, the differential form, your internal energy equals the change in heat plus the change in work. Now this is for molar systems. And remember, your internal energy is directly proportional and directly related to temperature. But since change in heat equals 0, your internal energy is only governed by the volume work, as the amount of work done in the system. So if you have a piston, the piston moves, you do work on the system, that is your only change in internal energy. Right? So imagine a piston with most efficient, 100% efficient insulation. So there is nothing coming in, nothing going out. So you just have so if you compress the system as a gas, you have heat. That works. Yeah. And the differential change in work equals PdV. So that your internal energy equals the negative of pressure change times the change in volume. think we've covered that quite thoroughly by now. So for an ideal gas, that becomes your change in internal energy equals negative of nRT over VdV. Now, remember your T is not constant and your volume is not constant, so you have two variables here. But your N and R are constant. Hence, from a heat capacity point of view, your change in volume can be, if you set your change in volume equal to 0, your CV equals du over dt. So your constant volume heat capacity is du, your change in internal energy over change in temperature. Hence your du equals CV dt. And rearranging that, you get du equals ncv dt. Remember Cm delta T, you've seen it all in physics before. So your heat capacity times the number of moles, or if it's mass-based times the number of the amount of your material times the change in temperature is your change in internal energy. So and since du for a constant volume system equals dq, then it's basically the change in energy, the amount of heat you put, for example, to boiling water. So du can be found for any process using this equation. For some reason, it's okay. And if you substitute du equals ncv dt into your previous equation, so your du equals nRT over V, you can balance that equation to be ncv dt. So for constant volume, that's one side of your equation. So where your volume doesn't change, and remember volume and temperature changes both at the same time, so you need to cover both. So ncv dt equals minus nRT over V dV. So with respect to change in volume on the other side of the equation. And dependency of change in temperature. So this is your dependency of change in volume and temperature. You have both sides. You can only calculate one at a time. But if you put them both in it, because energy cannot be created and destroyed, you can actually balance that equation. Yeah. If you integrate this, you'll get and put all your terms on one side. So 1 over T dt equals minus R CV 1 over V dV. So your R and CV, remember, are constant. You can integrate with respect to temperature on one side. So you get your change in temperature, 1 over T dt, and with respect to volume on the other side, 1 over V dV. And I think from there it's quite straightforward. Log of T2 over T1 equals minus R over CV, log of V2 over V1. Yeah? And if you solve for that, you can actually calculate T2 over T1 equals V2 over V1 to the power of negative R over CV. So at any point, if you have your initial temperature, your final temperature, your initial volume, and vice versa, you can calculate your new volumes for a adiabatic system. Again, if you remember, for an ideal gas flow, R equals Cp minus Cv. So if you substitute that into the previous equation, T2 over T1, V2 over V1, to the power of minus R over Cv, you can find the relationship with change in pressure, the heat capacity with change in pressure as well. So T2 over T1 equals V2 over V1, Cv over Cv minus Cp, which simplifies to V2 over V1, 1 minus Cp over Cv. You can then go on to find the relationship between the change in Cp and Cv. And the reason you do that, you can actually, and I'll get the fellow who's coming tomorrow to talk about this a little more. You can measure Cp and Cv in a system, and you can, based on that, or you can measure the volume and then calculate Cp and Cv, which are constants, and then use them for calculations, process simulation calculations. This is the very, very core and principle of that work. So you see them in, basically these are the kind of things that are done in background in Aspen, Pro 2, that kind of simulation software. And the heat capacity ratio is gamma equals Cp over Cv. This bit is quite useful, that I've seen them come up in exams quite often. So remember the ratio. So for an ideal gas, adiabatic compression and expansion, T2 over T1 equals V2 over V1 to the power 1 minus gamma, because Cp over Cv equals gamma. And for V1 over V2, it's gamma minus 1. So just swap around the powers. And T1 V1 gamma minus 1 equals T2 V2 gamma minus 1, and the general equation will be Tv gamma minus 1 equals a constant. Now, tomorrow we're going to go through quite a few examples working through these derivations, so you can understand the whole process a lot better. That's why I wanted the kind of workshop approach, so you get more time rather than just trying to memorize the equations. And if you compare isothermal and adiabatic processes, you'll find T is directly related to V minus gamma minus 1. So, and for an adiabatic process, so isothermal, you have constant temperature, as you can see, and for an adiabatic process, you have Tv gamma minus 1. That is your exponential ratio change. So it's Cp over Cv minus 1. Right. So if you, in a more of a real system, this goes more towards polytropic systems. If you change volume, you'll end up changing temperature if there is no exchange of heat. So there's no exchange of heat with the atmosphere. So remember PVT. So if you change any two parameters, you can only change two parameters at any point. You can't change three parameters, so you can't change only one parameter. So for a diatomic gas, your relationship becomes T directly related to V minus 2 over 5. And remember your rotations. So we'll go over this again tomorrow, but the reasoning is your rotations from heat capacity. If you remember what's Cv equals 5 over 2R and Cp equals 7 over 2R. So based on that ratio, if you reduce volume by a half, so if you set volume equals 0.5, you'll change that ratio, you'll increase the temperature by 1.32 times. Short lecture on adiabatics, and then we'll go through the actual derivations and why this works tomorrow in groups. So I'll get you guys in groups and get you to work through it together, and then we'll basically go around and help you out. Sound the same okay? Yeah? Alright. I'm going to go through, was that slower this time, by the way, or is it still quite fast? Still quite fast. Alright, but I think working through the actual equations will help tomorrow, because there's so much you can do here with just taking notes. I'll try this approach. If you seem to not like it, then we can go through doing it on the headboard. It's just something I found more useful when I was learning this, going through this slowly and then going through it with other people at the same time. So innovative teaching technique, peer teaching. You're going to be teaching each other, and then I'm going to go and basically teach the group, and also the other fellow who's coming over. You might have met him before. Yep. So shall we move on to the tutorial questions? Yeah. I'm going to give you 5 minutes to just think through it, and then I'm going to go over it with you guys, because I want to get through all the tutorials as quickly as possible so you guys can think through it. Everything's recorded, and if anyone has questions, by the way, and they don't want to ask now or later, you can actually email me. Just work through your tutorials, take a picture of your working and email it to me, and I'll either meet up with you guys, give a short lecture on it, or as I do, put a video up so it's useful to everyone. If you have a question, I'm sure 10 other people have the same question.